My name is Angelo Tartaglia, working together with Massimo Bassan, Giuseppe Pucacco, Valerio Ferroni, and Daniele Vetrugno. We are presenting here a proposal for an experiment in space to measure the gravito-magnetism originated by our galaxy, and having a special thought to LISA. In the first slide, you see the principle of this experiment. You have a triangle which is followed by light or electromagnetic waves in both directions, right-handed and left-handed. We know that if we have a reference frame and a choice of coordinates such that the metric tensor has non-zero space-time components, the two times of light in both directions, in two directions, are different, and the difference is given by this integral here. In the next slide, we see in more detail what I'm meaning. If we are in flat space-time, the result can be different from zero whenever the observer is with its reference frame moving on non-inertial motion. And this effect can be eliminated choosing appropriate coordinates or a different kind of observer. But if we are in a curved space-time, besides what I have mentioned now, we also have a contribution from the angular momentum of the source of gravity. In both cases, we see that we say that this is a Sagnac effect. In the first case, it is a kinematic Sagnac effect. In the second case, you have a gravito-magnetic effect, because in weak field approximation, the terms, which are time-space terms in the metric, may be read as the space components of a vector, 3 vector, which in turn may be considered as being the vector potential of a gravito-magnetic potential, analog of the magnetic field, which is the curl of the vector potential. Now, in the next slide, we see the situation of our Milky Way. In the Milky Way, we have to consider that the Milky Way is assumed to be immersed in a huge and massive dark matter halo. This is true for most galaxies. If the visible matter rotates, we expect also the halo to rotate, and this means that there is an important contribution to the angular momentum of the galaxy coming from the dark component. The metric tensor inside the matter distribution expresses a cylindrical symmetry about the axis of rotation of the galaxy. Furthermore, we may assume approximately mirror symmetry about the galactic plane. This is important since the solar system is approximately in the galactic plane. Now, let's go on to the next slide and formally calculate the gravito-magnetic field due to the angular momentum of the galaxy, both visible and dark. The formula is there. If we are in the galactic plane, the partial z derivative are all zero, which means that the gravito-magnetic field is perpendicular to the galactic plane and, of course, parallel to the z-axis. The time-of-flight asymmetry is written there. Using the Stokes theorem, we may convert the closed contour line integral into a flux of the gravito-magnetic field across the area which is contoured by the path of the electromagnetic signals. If we are in the solar system at the height of the Earth, moving around, you change the distance from the observer and the center of the galaxy, but the relative change is at most in the order of 1 part in 10 to the 9th. We expect the gravito-magnetic field 2 to change at most in 1 part in 10 to the 9th. In practice, we may assume that Bg is a constant, as well as U can be approximated to 1, and the result is that the time-of-flight asymmetry is simply the product of the gravito-magnetic field times the area contoured by the electromagnetic signals times the cosine of the angle between the axis of the contour we are using and the axis of the galaxy, plus other terms which include contributions from different sources, such as the sun, and of course, the kinematical Sagnac contribution too. Now, in the next slide, we see the configuration of LISA. LISA is a triangle, 2.5 million kilometers inside. The triangle is at an angle with respect to the galactic north, of course, and also to the ecliptic north. LISA moves along the orbit of the Earth around the Sun and follows the Earth at a distance of some 20 degrees. While moving around, of course, the angles change. There is an oscillation of the plane with respect to the direction of the galactic north. This means that the expected signal, the expected time asymmetry, is modulated yearly. Considering this, in the next slide, we show what we expect to have as signals. In the upper part, we have the Sagnac term. The Sagnac term, kinematic or Sagnac term, is due to the fact that the three space stations are orbiting independently from one another, but keeping a distance among them, not really fixed, but almost fixed, so that the triangle is preserved. The result is that in the oscillation, combined oscillation and motion of the space stations produces a shape like the one you see there over a time of a 4-year period from -2 years from now and next 2 years. Then we have what we can expect as signals from the sun, the red one, which is again also modulated because the axis, rotation axis of the sun does not coincide with the direction of the north of the ecliptic. Then the smallest contribution comes from the galactic gravito-magnetism, and in turn it is yearly modulated during the year. Now, the problem is that there is a difference in orders of magnitude, many orders of magnitude between the Sagnac contribution and the other two, the physical ones. This is the challenge we have to face. Next, I mentioned the fact in this slide, the technique to be applied is the so-called TDI, or time delay interferometry. It permits to simulate the behavior of our system, mimicking a Sagnac interferometer. This is for calibration purposes, and suppresses the gravitational waves, which is the main goal, of course, of LISA. But again, for calibration, you need to have something without this contribution. The TDI also serves to compensate for the fact that the triangle is not rigid. The distances are fluctuating. This is the flexing of the arms, and you have to compensate for it. Now, I mentioned another physical opportunity, in principle, which is the gravito-magnetic Faraday effect. It is the analog of the magnetic Faraday effect. Whenever light, polarized light, is moving along the lines of the gravito-magnetic field, we expect the polarization plane to rotate about the direction, propagation direction. And the rotation angle depends on the gravito-magnetic potential. This is extremely weak, but in principle, it is there. Finally, let me mention in this slide a few references where you can find more technical details. And this is all. Thank you.